All right. Hey guys. So I am working on recording the audio for um, our AP Environmental Science notes. So I am recording this right now. Hopefully it will work. This is just a test, but hopefully when I'm recording by myself, that will lead to you guys not getting like the really long version of events where people ask questions if you're looking for something fast. Now, I still highly recommend that you join me. I'll be live every day at 3, except for on Thursdays when I'll be live at 3:30. So without any further ado, let's start going over the Unit 9 notes. So even though the College Board has said that you don't need Unit 9, Unit 9 is basically a review unit. So we've covered 90% of this content before, and the College Board still expects you to be able to make connections across different types of units. And so I think that covering this unit will be in your best interest for the AP test, and I think it's probably the most important unit in all of AP Environmental Science. So we're still going to cover it. So starting out, the atmosphere is the thin layer of gases around the Earth, and those layers are sorted based on how heavy they are. So at the bottom, obviously the pressure is the highest. We consider this 1 atm, right? 1 atmospheric pressure, right? And that's about 13 pounds per inch. And that's the pressure you're under right now. But as you go higher up, the atmosphere is thinner because there's less stuff sitting on top of it, so it's less smushed, right? That's why when you go up in an airplane, you're up around 30,000 feet, and you need the compression in the airplane to make it so you have enough oxygen to breathe. This is why people who climb Mount Everest need like face masks that provide oxygen, and they carry their tanks up with them. Even though they spent time at base camp where their body acclimated to there being less atmospheric pressure and less oxygen, there still isn't enough at the top of Everest and other very tall mountains. Also, it is getting colder. Now, I know that that seems kind of counterintuitive because the sun is closer, right? So you would think it would be warmer, but it isn't. It's colder the higher up you go, because the less dense the gas is, the less likely it is to be able to, one, keep the warmth that it has, right? A light blanket is less capable of keeping you warm than a heavy blanket. And then on top of that, it is radiating heat out into space. So we lose most of the heat we get from the sun back into space, which is good. Because if we were at thermodynamic equilibrium with the sun, we would be the temperature of the sun and nobody would be alive. So the troposphere is the layer that you live in. We live in this area. All life is in this area. Okay. What this means is that there is about 70% nitrogen, diatomic nitrogen, completely inert. And then the rest of it is made up of mostly oxygen, right? Carbon dioxide, radon, like nitric oxide, sulfur dioxides. Those things are in way smaller amounts, though, than oxygen. And again, oxygen is actually a pretty poor greenhouse gas, but it is capable of holding on to some thermal energy. So that's something to keep in mind. So as you go up, you go from the troposphere to the stratosphere. The stratosphere is pretty high up, and that is where the ozone layer is. Now remember that ozone layer is made of O3, okay? And it does a really good job of protecting us from UVC rays. UVA and UVB still make it through, although that is what gives you a sunburn, so we know that UVC is stronger than them, and that is something you definitely don't want to hang out with for very long. It's why we have to have so much shielding on the space station. And why there is a sun visor on the astronauts' helmets that blocks a lot of that light. It's polarized, right? And so polarized means that there are two like layers in the glass that only allows light to go through that will fit through this wavelength, right? If you had something that was double polarized with rays going this way and going this way, you would get no light. Okay, so that's what we use to block the UVC for the astronauts, although they do have a higher than average occurrence of cancer and stuff. So we do know that we're not 100% efficient in shielding them. In the stratosphere, ozone is a good thing. In the troposphere, ozone is a bad thing, right? Because ozone is extremely toxic to breathe in. And we know that that is a secondary pollutant that comes from like photochemical smog and emissions from vehicles, okay? Higher up, you have the mesosphere. When you see a shooting star, it is because something has hit the mesosphere. It is, you can't breathe up here. You cannot breathe up here. And it's very thin, but it's still providing a huge amount of friction. So when you see like a meteor, like a shooting star, something the size of an SUV, a rock the size of a Suburban, could hit that and it would burn up to the size of a grain of sand. Okay. And then outside of that, you have the thermosphere. Again, this is the thinnest, lightest, coldest. You definitely can't breathe up here. And it's just providing that last level of insulation around the Earth. So moving on to slide 4, the stratosphere is very dry, right? There are not a lot of, like most clouds are in the troposphere. And then very little air mixing takes place between these things. That's how the ozone layer stays up in the stratosphere and doesn't come down to the troposphere where it could hurt us. So looking at the atmospheric gases, again, this should be a review. It's 78.1% nitrogen, 21% oxygen, 0.3% argon. And then there's a bunch of other gases that make up such a little percent that we're not even going to put a number on them, right? Carbon monoxide, carbon dioxide, methane, nitrous oxide, ozone, CFCs. Remember, those are things that are artificially created. They're usually used in refrigerants, and water vapor. Okay, even though you think about water vapor taking up a huge amount because you think about like the humidity level. Well, when you think about 100% humidity, that doesn't mean that the air around you is water. It means that it has reached the maximum amount of saturation that water can stay in the air, right? Because if it gets too heavy, if it gets over 100%, it rains, okay? So the greenhouse effect is when the sun radiates heat down onto the Earth, and then some of it bounces back into space, but some of it doesn't. Okay, so let's talk about that. We're on slide 6. We need some greenhouse gases, okay, to be 100% clear. Having no greenhouse gases would kill everyone, partially because water vapor is a greenhouse gas, right? And that is something that is going to hurt you to have no water vapor. If you've ever lived somewhere extremely dry, you know what I'm talking about. You get dry skin, your lungs can get irritated, your eyes, right? You're counting on that moisture. That's why when you breathe in and you breathe out, that's why that air is warm and humid when it comes out, because your body needs it to be warm and humid or it will dry out your lungs, right? And also, the reason that it's not no degrees at nighttime is because the atmosphere is holding on to heat for you, okay? So the reason that daytime temperatures and nighttime temperatures don't vary by hundreds of degrees is because of the greenhouse effect, okay? So when we're looking at that, right, the solar radiation, let's take that 100%, right? 50% of it hits the surface of the Earth and is absorbed by the ocean or by the land. Now, land is not as good at absorbing radiation as water is. Water absorbs thermal radiation better than anything else in the universe. That is why it has the highest specific heat. You might remember that term from chemistry or earlier in this class. That is why places that are further inland have much more dramatic temperature swings between day and night, whereas places that have a large body of water, such as the Great Lakes, an ocean, or even a large river, will have a more stable temperature, because during the day, water is absorbing that heat, and at night, it slowly releases it. Again, very slowly, because it has the highest specific heat. Okay, 5% hits the land surface and just bounces straight back up into space, okay? That is largely due to a phenomenon called albedo, which we're going to talk about in a minute. 20% of it, 20% of that 100% coming from the sun, is absorbed by clouds in the atmosphere. So that means that clouds are getting heated up, and that is part of what causes precipitation, right? Because it will cause that to condense, and then once it's condensed enough, it precipitates out, okay? 20% of the sunlight from the sun just bounces straight off the top of the clouds. The clouds are white, right? And white is reflective. Black is absorbent. So it just bounces straight off, goes straight back into space. And then 5% is just it's backscattered into space by the atmosphere. This is what causes the sky to look blue. It's called Rayleigh scattering. And because our atmosphere is heavy in oxygen, it is blue in color. So the greenhouse effect is the absorbing and re-radiating. Okay, so when something hits the earth and the surface warms up and then it re-radiates, that's the greenhouse effect. When something hits a cloud and it reabsorbs, that is the greenhouse effect, okay? However, there are some things that are much better at this than others. Some examples: carbon dioxide, methane, nitrous oxides, and CFCs are really good at holding on to heat. And what that leads to is sometimes you end up with too much heat absorbed, okay? And so the greenhouse effect keeps Earth's temperatures within a habitable range, but if we shift the atmospheric percentages too much, what you're looking at is too much heat being absorbed and the average global temperature increasing. Now, we've talked about in the past how things like the Gulf Stream being disrupted can actually lead to some places experiencing a cooling effect, while the rest of the world is experiencing a warming effect. So it won't get cold everywhere at the same time or warm everywhere at the same time, but we are changing the equilibrium that our planet has had for the last several thousand years, okay? So water vapor is a greenhouse gas, okay? And it is responsible for keeping the earth warm. I'm on slide 8. Just like liquid water is very good at having a high specific heat and retaining heat, so is water vapor. It's made of the same stuff, right? And it can easily fall into a positive feedback loop that is shown right here. Okay, so I'm looking at the picture on slide 8, and I'm talking about how higher temperatures increase evaporation. More evaporation leads to more water vapor, and then water vapor that is now in the atmosphere traps more heat. Well, it's hotter, right? So there will be more evaporation. And because there's more evaporation, there will be more water vapor in the atmosphere. And because there's more water vapor in the atmosphere, you trap more heat and it keeps feeding itself, right? That's the fundamental difference between a positive feedback loop and a negative feedback loop. Because a positive feedback loop is going to loop through and then eventually shut itself off. A positive feedback loop will do the opposite and will keep getting worse and worse and worse, right? Also, water is not equally distributed across the Earth's surface, and therefore the heat produced by it is not equally distributed across the surface. And so that is why coastal communities will face like bigger impacts than inland communities, although inland communities already are dealing with a bigger swing in temperature between night and day. So the greenhouse effect, we call the ability of each gas the global warming potential. So I'm on slide 9 now. So carbon dioxide has a global warming potential of 1, okay? That means that it is capable of increasing the atmospheric heat retention by, I think, a degree every 100 years, okay? Now, in order to do that, you have to put a ton of CO2 into the atmosphere. Unfortunately, we are currently putting a ton of CO2 into the atmosphere every year. As a matter of fact, we are putting an amount that can be measured in gigatons, right? And I don't mean ton literally, I mean metaphorically a lot. But we are putting literal gigatons into the atmosphere every year. And so per 100 years, we are raising the global climate by a degree. Now, if we were doing the same thing with methane, that would have a global warming potential of 28. Oh my God, I'm gonna sneeze. Okay. Now, we don't tend to just put methane into the atmosphere. When we use methane, now some of it escapes. We talked about that during fracking, how the gases can escape out of the ground once we've cracked the bedrock, right? There's also methane stored from dead animals decomposing at the bottom of the ocean that bubbles up to the surface. Like there is some methane getting into the atmosphere. However, right, we burn methane before it gets released into the atmosphere. We get energy from it. And when you burn methane, it turns into CO2. Okay? Nitric oxides and CFCs are very good at causing an increase in temperature. They are really good at distributing heat throughout the atmosphere. Okay, and so that's why those things have a higher global warming potential, a lot higher. If you're looking at this chart, you're looking at numbers in the thousands, whereas CO2 is in the one. It's one, right? However, we put a lot less of that stuff into the atmosphere. Think about it this way. What do you do more often? Cause a leak in your refrigerator that causes CFCs to leak into the atmosphere, or drive a car? Right, your refrigerator wouldn't be working if it was leaking. So, all right. Now we're looking at slide 10. So Mars has a much thinner atmosphere despite the fact that it is way higher in CO2. A hurricane strength wind on Mars would not have the power, the inertia to knock over a tent. Okay, so while it's much higher in CO2, it has just way less mass. And that decrease in mass leads to a lower effect. The Martian daytime summer is around 70 degrees Fahrenheit, but the same location would experience a negative 100 degrees Fahrenheit temperature at night. So it's just something to see. We do need some greenhouse gases, okay? So let's talk about stratospheric ozone. We've talked about this a little bit before during our air pollution unit, but let's talk about it in more detail, okay? So a few fun facts about ozone. In the troposphere, it is critically dangerous. It can cause coughing and wheezing at low levels, permanent lung damage, and increases your risk of lung infection. If you've been following the news at all, you can tell, because coronavirus causes a lung infection, right? That lung infections are extremely dangerous. You can need to be put on a ventilator or a respirator, both of which we do not have many of, right? And it can cause permanent scarring and damage. We've talked about how those alveolar sacs are easily decayed by the immune system. And because when they decay and they merge into one cell instead of a bunch of little grapes, right, it has a lower surface area. So the ability of your body to absorb oxygen is diminished when you're exposed to things like ozone. However, in the stratosphere, it's super vital, okay? But if you were up over that, you would be at risk. If you were over the stratospheric ozone layer, you're at risk of cataracts, cancer, and skin damage, okay? So molecules like CFCs, I've moved on to slide 13, they bind to ozone and break it into like a chlorine oxide or a O2, so diatomic oxygen, right? What we currently breathe, O2, right? And we erode that layer that's protecting us from like cancer, eye damage, skin damage, right? Those things that UV radiation breaks your DNA, right? So it's tiny. It gets into your cell and it bounces around in the DNA and it breaks nucleotides, right? It breaks them apart. And maybe your body will fix it. I have had many a sunburn in my life and my body fixed it. But every time you break something, you're risking that it will be repaired badly. And when you get a sunburn, you're damaging thousands or millions of cells, okay? And so you're giving your body millions of chances to make a mistake. All right, so we don't want UVC radiation down here in the troposphere where we live. And so before the Montreal Protocol, slide 14, of 1987, we were exponentially increasing the number of CFCs that were being released into the atmosphere. Okay, and so part of the reason that happened is because everyone got a refrigerator, hairspray, when you have a pressurized can of like bugs and stuff. Now, when you look at your pressurized can for killing wasps, or your pressurized can that cleans your keyboard, or your pressurized can of hairspray, now they use inert gases to pressurize that container, but they used to use CFCs. And so people were using them. They would be released into the atmosphere. And then eventually, if they ended up on that upper edge of the troposphere, the lower edge of the stratosphere where the two touch, it would bind with an ozone molecule and produce oxygen and a chlorinated monoxide, right? Which is muy triste, okay? So I linked to an article on this that is by PBS. It's a really good article, and it talks more about that in detail. I know we've talked about this before, so you guys might not be like super keen on looking on that, and that's fine. But if you need more information, the Montreal Protocol is one of the things you have to have flat memorized for the AP test. It is one of the 12 pieces of legislature that you have to know, because it's one time where we showed that the world can really come together and just be like, nope, not anymore. We're not doing this anymore. And all of these CFCs, which stands for chlorofluorocarbons, right? Or bromol carbons if it's made with a bromide, or it can be chlorinated, it can be carbonated, it can be made with a bunch of different chemicals, right? Long story short, they're supposed to be entirely phased out by like 2050. Okay, now we needed to give people time to phase them out, right? Because you can't just be like, every person in the United States needs to buy a new refrigerator tomorrow, right? You can't even be like, every person in the United States needs to buy a refrigerator by next year, right? People don't have that kind of disposable income. But they're slowly phasing it out. It's getting harder and harder to buy. They regulate the industry, and if you can't buy it, people have come up with alternatives. Okay, so one thing to keep in mind is that CFCs have been replaced by HFCs, which don't break the ozone layer, but are still a powerful greenhouse gas. Okay, so this is not dissimilar from when everyone was like, oh my God, plastic straws are killing the sea turtles. I'm going to get a metal straw, or a hard plastic straw, like this. Well, the problem with this is that if I throw this away and I don't keep it for years, right, it's replacing a bunch of plastic straws. But when this goes to a landfill, it still causes a problem. Metal straws are even harder to break down. This is going to take forever to break down a landfill. That's why I'm going to keep it for a really long time, right? It's the same thing with reusable grocery bags. Unless you're using them every week and you don't forget them, eventually your canvas bag will end up in a landfill. Now, canvas is pretty harmless. It breaks down pretty quick, but some of the reusable bags are still made of plastic. Okay, so sometimes you replace something with something else, and it's a good idea and you're doing the right thing, but it's still not a permanent solution. And that's what we're looking at with the CFCs being replaced with HFCs. Okay, all right, so let's look at the history of Earth and her climate, because a lot of times when you talk about climate change, people will be like, well, it's been hotter than this before, or it's been colder than this before, and they're not wrong. Okay, they're not wrong. The Earth's climate has changed, but usually it changes because kids who are in my astronomy class hopefully know that the Earth's orbit around the sun isn't perfectly spherical. And sometimes it'll be closest to the sun and summer in the northern hemisphere at the same time every, couple thousand years, and it will cause an increase in global temperature. We're not talking about that right now, right? There's also cycles that we're going to talk about that the Earth goes through where there will be more flora than usual. And so we'll produce more oxygen, and oxygen is a pretty crappy greenhouse gas. And so we'll have a global cooling period. That's what ice ages are. And then ice ages kill the flora, the plants, right? And so then what you end up with is less oxygen. And as a matter of fact, as those plants die and they decompose, they release carbon-based gases, and that warms it up. And so we usually have this cycle, but this cycle usually takes tens of thousands or hundreds of thousands of years. So let's look at it. Slide 17. Let's talk about the Precambrian period. All right. During the Precambrian period, which was 4.6 billion years ago to 540 million years ago. Okay, that is a big, that's a big chunk. Okay, that's a big chunk of Earth's history. The atmosphere was mostly carbon dioxide and nitrogen instead of being mostly oxygen and nitrogen. And part of the reason for this, guys, is that oxygen is actually toxic. Okay. Oxygen causes something called oxidation. Okay. Rust. Oxygen causes fires, right? Fires can't exist without oxygen. Oxygen slowly damages cells. It creates something we call free radicals, which can be pretty dangerous, okay? Oxygen is not good for everything. And most types of life that exists on Earth between 4.6 billion years ago to 540 million years ago did not use oxygen to produce energy. Okay, you, a human, and all other animals and most plants use oxygen to create energy. It wasn't like that before. And as a result, there was a big limit on how much energy you could accumulate, right? The mitochondria wasn't a thing. Well, the mitochondria is responsible for 32 out of 36 ATP produced by your body. So now you're operating on 4 instead of 36. That's not a good thermodynamic equation. You're not getting enough bang for your buck without oxygen, okay? And so life couldn't be bigger than single-celled, right? Look at this beautiful kind of green ocean. Now, this is actually a picture of a cyanobacterial bloom on Lake Erie, but this is what scientists think the oceans were full of this type of cyanobacteria that was the game changer, so to speak, okay? So cyanobacteria evolved the ability to perform photosynthesis, all right? They could take in a carbon dioxide and they could make it into sugar, into glucose, and keep it for energy storage later. That is like such a game changer. That is more of a game changer than inventing computers. That is more of a game changer than inventing a combustion engine. This is more of a game changer than inventing fire or the wheel or anything. Okay, this changed how all life on Earth would have to respond. Here's why. Because in the process of taking a CO2 and turning it into a glucose, they ruined the atmosphere for everyone else. They made the atmosphere oxygen rich, and oxygen was toxic to all forms of life other than them. Okay, so they became the dominant species on Earth by killing everything else with their waste product. Okay, and so that photosynthesis replaced the warm CO2, like the warming, the global warming potential of 1 CO2, with oxygen. And so the Earth froze. The whole thing. Now, the oceans didn't freeze solid. That's how life survived, if you're wondering, right? Oceans, because of this, is actually one of the most important things to life on Earth. Ice floats, right? And because ice floats, it then insulates the rest of the water body from being frozen solid. And this is how life survives during the winter. And my dog is losing her mind at a bark. Hold on. George. Well, there's just some poor girl walking her dog that just got barked at by my dog, so it's pretty cool. George, I swear to God, come here. Okay. So, anyways, because of this, the Earth was insulated, but it did kill a bunch of the cyanobacteria. It's almost like, hear me out, right? They produced a byproduct gas that overwhelmed the atmosphere and changed the climate so they could no longer survive. When have we heard that before? Cough, wheeze, climate change right now. All right, so they caused such a radical shift in the Earth's insulative layer in the atmosphere that it froze the entire Earth solid. We call this snowball Earth, okay? So this was the first and longest ice age. So now let's transition to slide 19. There have been several. Okay, there have been times where it is a lot warmer, and there have been times where it is a lot colder. All right, the Earth has experienced at least 5 major ice ages. But I want you to look at the scale. Okay, I want you to look at the scale of this graph, and I want you to realize that the timeline that this has happened over was millions of years, hundreds of thousands of years. Whereas we have changed the Earth's climate in 50 years, right? Maybe 100. If you want to start in 1900, right? When the Industrial Revolution left England and hit the rest of the world, you're talking about 120 years instead of 120,000 years. We are doing the same thing 1,000 times faster. And the thing to keep in mind here is like life on Earth will probably survive. It will. Right? It survived all these other ice ages and all these other warming periods and all these other things, right? But life on Earth doesn't have to mean humans. we have developed the societies that we have right now on the backs of agriculture. Well, most of the things we grow need a very specific growing climate. They need a certain humidity, a certain rainfall, and a certain global temperature in order to survive. That's why sometimes there's a freeze kind of late in March and it kills everyone's plants that they just planted. Okay. That's why when there's a really long, hot, dry summer, trees will die in people's yards, right? Or in my case, all of my grass. Okay. Just because life on Earth will survive doesn't necessarily mean humans will. And so it's something to keep in mind when we are changing the climate thousands of times faster than it's changed before. You are so right. It has been warmer before, but there weren't humans. And it has been colder before, and there weren't humans. Okay. So that's just like thinking of things that people usually say back to me when I'm like, oh, climate change is kind of a big deal. And they're like, no, it's not. And I'm like, oh, God, help. Okay. So moving on to slide 20, we call these things glacial periods, i.e. when there are glaciers, and interglacial, Jessica, speak correctly, periods, okay? And so when the climate is warmer, the glaciers retreat, okay? During a glacial period, there will be a mile of ice over Boston, okay? There will be glaciers all the way down to like Kentucky. That's wild. Okay, we are currently in an interglacial period, as you've probably noticed by the fact that Kentucky is not frozen solid. Okay, and so this graph shows that glacial versus interglacial period, and it shows that they're not always regular. Okay, they're not always consistent. They can be caused by the Earth's orbit changing, it can be caused by the solar output changing, and it can be caused by a change in the dynamic of the flora and the fauna on Earth. But again, those changes aren't fast. You're looking at hundreds of thousands of years to get this done, okay? And we are going full speed. All right, so how do we know? How do we know that there was more CO2 in the atmosphere last time it got warm and there was more oxygen in the air last time it got cold? Okay, we measure those things by proxies. What that means is we go somewhere that humans are not allowed to touch, mainly Antarctica, sometimes Greenland, okay? And we take a giant screw and we core down into a glacier where nobody has walked and nobody has touched and nobody has messed up the data for millions of years. Nobody ever lived on Antarctica, okay? So we have an undisturbed, pristine sample size. They take that core and then they analyze it. And you can actually tell. I don't know if you've ever lived somewhere cold, but it'll snow and then it will get a little bit warm out and it'll be sunny and clear. And like the top layer of snow will kind of crust over as it melts and then refreezes. And then it will snow again. And there will be layers in the snowbank. Okay. Now imagine that that has been going on, not melting and not being disturbed for thousands of years. Okay, so we have an undisturbed sample of what the snow is like, but snow and ice are not solid. There are pockets of air. So what we can do is we can take these ice cores shown on slide 21 and we can look at them and dissolve them and see how much oxygen is in them and how much carbon dioxide is in them and look at the balance, okay? And so two sets of data can be analyzed: temperature, by looking at the relative amounts of oxygen. And then you can tell how much CO2, methane, and nitric oxides, which are the three major components of global warming, are present as well, okay? Because when the ice is being stacked and stacked and stacked and stacked and crushed into this sheet, this glacier, pockets of air are getting stuck in there. And if we seal them up, we can see what's in there, okay? Just like if you were looking for fossils and you found it in a particular layer of dirt, you would know how old the fossil was. Okay, so this slide shows the CO2 change over time. This is data we got from the proxies to the temperature change. Okay, so this is slide 23. Is this graph perfect? Absolutely not. Okay, correlation is very strong. Strong enough to suggest causation, okay? Because every time the global temperature drops, the CO2 level drops, we think they're connected. because every time the global temperature increases, increases, the CO2 increases, we think they're related, okay? And not only that, so that's one piece, right? That is the correlation argument. We also know the exact chemical reaction that is happening in our atmosphere that is causing the heat to stick around. So then we have the mechanism. And when you put those two things together, it makes a very strong argument, okay? And like, I'm not going to sit here and tell you. I'm not going to sit here and tell you that we might never find a piece of data that conflicts with this, right? We might never find a piece of data that shows a different causation. But we haven't found one yet, and we've been looking really hard, okay? So that's just something to keep in mind. Like, I am the first person to say that if NASA comes out with new data tomorrow and I look at it and they've provided a mechanism and correlation and proxy data and all the stuff that we have, I would change my mind. But I would change my mind because this data is very good. And if you could give me an equivalent, I would believe it. Okay. Also, you can look at the methane correlation and it's very similar as well. Mainly because when you get a spike in CO2, you also usually get a spike in methane. Although if you look at the main difference between slide 23 and slide 24, at the end of slide 23's carbon dioxide meter, you see a exponential increase, right, in CO2. That's because of combustion. That's because of humans burning fossil fuels. When you look at the methane number, it's not as dramatic. And the reason for that is we do not just throw methane into the atmosphere. That stuff is useful. We burn it on purpose, okay? And then it turns into CO2. The reason that methane is naturally occurring in the atmosphere is because things decompose. And when those things die and release their CH4, like the off gas, you guys know, like dead bodies produce off gases. Well, so do dead plants. So does dead everything, right? Everything releases gases of what it's made of. And because life on Earth is made of carbon, it releases CH4. Okay, and so that's what you're seeing there. All right, the last glacial period ended 10 to 20,000 years ago. Okay, this shows the dramatic increase in temperature and CO2 that has been coming since humans were around. Okay, so humans in their current form have not existed for longer than like 20,000 years. And when we say in their current form, like you're definitely looking at hunter-gatherers until like 4,000 years ago, 6,000 years ago, okay? And even once humans got out of their hunter-gatherer stage, which they probably got out of because the world naturally warmed, okay? Things were relatively normal. They were relatively stable. I'm looking at this line between 10,000 and 100, because this is a log scale, so it increases by a power of 10. Between 10,000 and 100, I'm looking at that, I'm like, that's pretty stable, man. And then about 100 years ago, humanity invented combustion engines. And look at that exponential increase. Okay, so that's just something to keep in mind. All right, there was a medieval warming period and a medieval little ice age. The medieval warm period lasted from 950 to 1250 CE, which is AB, for those of you who don't use BCE and CE, Common Era. And we think that this is why the Vikings were able to cross the Atlantic Ocean, because there was not a lot of ice in the way. Right now there's ice in the way. And that caused them to colonize Greenland and Newfoundland. And also, you look at the population of the world, and it increased during this time because people were able to grow more food. Okay, and so it's just something to keep in mind. Throughout Europe and Asia, you saw an increase in global population that was correlated with warmer temperatures, higher CO2, good for plants to a point, right? Warm CO2 is good for plants until it's on fire. Okay, cool. The Little Ice Age lasted through the 16th through 19th centuries. So this is when you see the Viking colonies in Greenland stopped being a thing. The North American Indian tribes were forced to form alliances because they were so short on food. that they were like, I guess we're not blood enemies anymore. Okay. The River Thames in London would freeze like all the way over, and people would like go have a county fair on the river, which is kind of hilarious in my opinion. It doesn't do that anymore. And a strait called the Greenbelt froze over, allowing Sweden to march across it and invade Denmark. So there are human events tied to climate change, okay? Now, there are a lot of natural causes to climate change. So I want you to look at this, right? And I think the coolest thing about this graph is that it is very cyclical, right? You can tell exactly what it's supposed to do, when it's supposed to do it, okay? And we call that the Milankovitch cycles. So the shape of the Earth's orbit around the sun is irregular, roughly once every 10,000 years. The tilt of the axis wobbles about once every 23,000 years. And the axial tilt changes over about 41,000 years. So you're looking at tens of thousands of years, right? And we call those things precession, obliquity, Jessica, eccentricity, solar forcing, and glaciation. Okay, so when we look at the glaciation, we can see that it is responding to those forces from outside. And we would think that this is a very normal, very regular cycle. When I look at that, I see a very normal, very regular, very predictable cycle. And that's why there's like a sense of alarm, because in all of the Earth's history, it was cyclical and regular and predictable, and now it is not, right? And this is maybe a case of the devil you know beats the devil you don't. Also, fun fact, there are natural causes to CO2, methane, and sulfur dioxide being in the atmosphere, and they're called volcanoes. So on slide 29, you get a cute little picture of Mount Tabora in Indonesia, and it caused snow to fall in June. The reason that happened is because the ash blocked out the sun and it was cold. That's kind of crazy, right? The scattering of solar radiation that they produce is usually much stronger on a local level than the CO2 and the sulfur dioxide they're releasing is on a global level. So that's just something to keep in mind. I think that's super interesting. And that there are natural causes to some of these gases. Also, sunspots are a thing, okay? And sunspots are darker areas on the sun's surface that are created by intense magnetic fields. And you might think, oh, a dark spot, the sun is going to be colder. Wrong. Okay. This is one of those things that gets me every time. When there's a sunspot, there is more radiation, so it is hotter. However, the number of sunspots is also cyclical. So every 11 years, you'll see an increase and a decrease in solar temperature. Like, it's predictable. Where the sunspot will be, not predictable. The amount of radiation it will produce, yes, predictable. Okay? All right. So slide 31 is kind of a transition into a new topic. So I'm going to stop recording for now, and I'm going to try to upload this, and we're going to see how that goes and whether it needs to go on YouTube or if the file is small enough to fit in Canvas. And we're going to start talking about the Great Ocean Conveyor Belt and how it regulates the Earth's temperature tomorrow in class. Go team! All right. Let's go ahead and end the meeting. Oh God, how do I do this? All right, bye guys. Adios.